All right, so welcome. This is our presentation on amateur radio satellite communications. We are teachers in space. We provide professional development for K through 12 teachers all across the country. This past summer, we provided some workshops in New Mexico to show teachers how to build CubeSat emulators that they would then build with their students. They send those back to us, and we fly those and collect data. But in addition to that, we also launch orbital CubeSats, and we work with other organizations that launch orbital CubeSats. And on board most CubeSats is some form of radio communications. In in our CubeSats and a good number of other ones, especially university built CubeSats, they integrate satellite communications through amateur radio so that anybody with an amateur radio license can communicate with the satellite or at least collect data from the satellite. So these are CubeSats. They come in all sorts of different form factors. The ones that you see on your screen here are called a 1U CubeSat. So the form factor is a 10 centimeter cube, and a single 10 centimeter cube would be considered a 1U. If you were to say stack two of them on top of each other, you would then have a 2U. Put three on top of each other, you have a 3U. You could put two 3Us together, next to each other, and that would be considered a 6U. And there are all sorts of different combinations on top of that. So we work with the 1U because it's the simplest, and also because we can fit the most payloads on the various flight platforms that we work with. Some of those flight platforms you can see here. You can see on the right, there is a high altitude balloon. And then in the bottom left is the Perlin Stratospheric Glider. We also fly them on various other types of aircraft and on various rocket platforms as well. So here is an example of the 3U. This is our Serenity orbital satellite. And I'll go into a little bit more detail later, but you can see that yellow thing on the side there, that's the antenna. And it has some onboard experiments, a radiation experiment, and camera, and some other sensors as well. So just talking about, starting at the basics with radio communication, um, we talk about various types of visible and non-visible um, forms of radiation. You have everything from very low frequency down to 10 hertz, all the way up to cosmic rays that come from various objects in space. Part of those wavelengths are the visible light spectrum, which you could see kind of towards the middle here, which is actually a very small portion of you know all of this whole spectrum here. So part of the spectrum that we're going to talk about is the radio spectrum, from very low frequency up to extremely high frequency and everything in between there. So shorter wavelengths equal higher energy. And you can see in this image here that there's a little bit of like this wave shape here. These are the actual wavelengths, or a representation of the wavelengths. And so the idea between shorter wavelengths equals higher energy is that what you're doing is you're packing more of that energy into a shorter period, or a shorter distance right there. So it's just, you're going to have more energy in a shorter amount of time. Whereas, if you have a low frequency, just as the term frequency implies, you're going to have less of that wave in that same period of time. So essentially, a radio wave is a combination of a magnetic field at a right angle to an electric field. So you've got both of these, phenomena happening together, electric and magnetic fields. And, they are moving in waves in the direction of propagation. So the direction in which the radio is being broadcast. So, in order to pick up these radio waves, you need an antenna. And there's all different varieties of antennas out there. We're not going to go into too much detail just because there's so many different types. We'll talk about antennas that are specifically used in these applications. And interestingly enough, I said I would mention that antenna a little bit more on Serenity. It's actually made out of tape measure. So if you look closely at these images, you can see this yellow right here. This is the antenna on Serenity, and this is a DIY um, Yagi antenna that somebody made, and all they did was just cut up some tape measure, and you can use that. It's used pretty frequently because it's easy to work with, it's inexpensive, and it is foldable. So the way that the antenna on Serenity works, there's actually a little piece of nichrome wire attached towards the bottom, and there is I think it's a resistor that heats up and melts the wire once Serenity is in space and ready to deploy the antenna. And so when that wire gets heated up, it eventually melts. And then this, like if you have worked with a piece of tape measure before, it'll then uh, become rigid and it'll kind of like unfold out all on its own. So there's all different types of antennas from extremely expensive to extremely inexpensive and DIY type things. Now, of course, just like everything, the more you spend on something, generally, the better it'll work out for you. But we also want things to be as accessible as possible, so we want to offer all sorts of ideas. So radio wave propagation depends on the type of frequency that you are using, and the type of frequency you use is going to be dependent on what your application is. So here is just a little representation of a few different types of propagation. So we have our radio station here and an antenna. And so depending on the types of use case is going to be which actual not only use case but also the equipment that you have available to you will determine how your radio waves propagate. So very low frequency to medium frequency are called ground waves because they will actually follow the topography of the land. They can actually go up and over some obstacles versus a high frequency, which will just kind of propagate out in every direction and will often be blocked by like physical features like mountains and whatnot. But one of the features of them is that they can bounce off of the ionosphere. And so here we see like the examples. We have a receiver on the right side here. A ground wave could potentially go up and over a mountain and reach that receiver, whereas a high frequency radio signal, it would get hit, it would hit these mountains and bounce off or be absorbed and wouldn't hit that receiver. But depending on your space weather, which we'll talk about a little bit later, you can actually bounce that signal off of the ionosphere and have it come back down here behind that mountain. And then for um, you know applications such as deep space exploration or deep space probes, interplanetary probes, or space missions, you would want to use very high to ultra high frequencies, which can pierce through the ionosphere and not bounce off of it, so that you can get past that out into space. So this is a little bit more talking about the ionosphere and bouncing radio waves off of it. There are different regions of the ionosphere, and different types of frequencies can be bounced off of them, depending on the intensity of solar activity. You can also bounce radio waves off of the Earth's surface as well. You can actually skip a radio wave multiple times by bouncing it off the ionosphere and then down onto the ground and then back up to the ionosphere and down again. Um, it's possible to communicate all around the world by using these types of techniques. Um, it takes some skill, it takes certain conditions and certain equipment, but it can be done. So here is a little bit more on that phenomenon of the ionosphere, as well as how it can be affected by the sun. So you can see here, in the nighttime when the sun is not directly, or at least the night part of the Earth at that time is not getting direct solar interference, versus in the daytime part, it can actually cause the ionosphere to fluctuate, and you get multiple regions that might be affecting your radio waves in different ways. So some of the things that will affect your radio propagation, as I had mentioned, was solar activity. So from solar flares and sunspots, those can have effects on it. Auroras, which are also connected to solar activity. You know, uh, Solar particles hitting the ionosphere excite various atoms and whatnot, and cause these beautiful visuals, but also can have effects on radios. So a tool that many radio operators use is NOAA's NOAA's space weather page, and you can actually click on this in the presentation. It'll bring you right to that page, and it'll tell you, what upcoming and current space weather is looking like at the moment, and you can get an idea of when will be good versus not so good times to be, trying to do different types of wave propagation. So a type of amateur radio that we use pretty regularly, and some of you have already experienced, actually many of you have already experienced in our workshops, is what's called APRS, or Automatic Packet Reporting System. When we do high altitude balloon missions, this is our primary method for tracking the payloads on those missions. So along with the CubeSats that we fly, we include an APRS tracker. And what that does is it sends out regular radio bursts with information about that tracker on it. So basically, what you do is when you order one of these trackers, you give them your amateur radio call sign. They program that in, and then what it will do is it'll send out every minute or so that call sign with a little bit of other information, including its location, latitude and longitude, as well as speed that it's moving, altitude. And so it's really helpful for um, keeping track of not just your high altitude balloon mission, but all sorts of different usages as well. So if we click on this, this will bring us to aprs.fi. This is the website that you use to track. So any APRS signal will go to numerous APRS receivers and repeaters that are located all over the country. And so if there's an APRS signal getting transmitted out there, it'll get picked up by one of these receivers and automatically uploaded to this website. And so people use this for all different reasons, whether it's just, they put it on their house, or they put it on their car, or boats, or aircraft. Like this right here looks like this is somebody's car. So yeah, currently it's at 682 feet of altitude, and this is gives you time, date, and then it looks like this person has keyed in that they're on their way somewhere, so they're en route. I know that. So this is showing where I'm at, which is in northern New Jersey, but in southern New Jersey, right around here, there is a ferry line that goes from the tip of southern New Jersey over to Delaware. And I know that these this ferry service uses APRS to keep track of the various ferries as they go back and forth. I don't know if there's any actually running right now, but I have seen in the past. So it's an interesting website. You know, you could go on it, go to your location, and you can see all sorts of different APRS signals in your area. I mean, you could just see how many there are. You know, the this is the New York, New Jersey, Philadelphia area, so of course there's tons and tons. Um, but your area might be a little bit different. Yeah, zooming out, it starts slowing your computer down because there's just so much going on. So it looks like maybe not so much going on here in eastern Montana. A little bit, but yeah, very useful for tracking things. We also use it on orbital satellites as well. So what you can do with APRS is you can encode data into uh, audit, auditory tones. So what happens is the data gets converted into a tone, which is then transmitted with radio. It is then picked up on the ground by a ground station, which then reconverts it back into data, and that's how that data can be transmitted. So this is what it'll look like. So these are this was a high altitude balloon mission that we did up in New York State, and it took off from the left side here. And it's kind of hard to see on this picture in particular, but each of these is it's like a little triangle, and each triangle is when one of those APRS signals was transmitted out. And what you can do is you can on the APRS website there is an option right here, Google Earth KML, where you can automatically download a KML file, which is a Google Earth file, and import it into the Google Earth software, and it'll make one of these images for you, and so you can see exactly where your APRS tracker was throughout its flight, and it shows you the altitude that it was at, as well as time and speed. If you were to open this up in Google Earth, you'd actually be able to click on each of these little points and it would give you a little bit of information about each one. So this is really useful. You can zoom in to where the last radio signal was sent out, and that's generally a good indication of where your payload is going to be. There's all sorts of different ways of receiving these APR signals. You can get accessories that plug into handheld radios that can convert the tones into data, and then using Bluetooth can send it right to a phone, or you can use that website that I was showing you, the aprs.fi. So ultimately, when you're receiving signals, especially if you are in a fixed location, we would refer to that as a ground station. And there are all different types of ground stations, everything from a handheld radio all the way up to the very large array, which is in New Mexico, actually, part of the SETI program, I believe. New Mexico folks, correct me if I'm wrong, but that's used for just listening to all sorts of signals that come from space, whether they are created by natural phenomena like pulsars and quasars, or looking for artificially created signals potentially from some extraterrestrial intelligence. So SETI is the search for extraterrestrial intelligence, and it's been working for a while now to see if we could detect any radio signals from some other world, some other civilization. There's a great movie about it called Contact, based on a great book. So definitely check that out. Carl Sagan wrote that book. Amazing individual. So here's what I was saying about ground stations can also be as simple as a handheld device, handheld antenna, and some handheld radios, or it can be made up of a computer with a accessory called a software defined radio and an antenna. And if you came to any of our workshops, you would have been given one of these SDRs, as they're called, and the antennas. So essentially, a software defined radio or an SDR is a little accessory or a dongle that you plug into your computer. You then connect it to an antenna, and then you open up SDR software and you can listen to all sorts of different radio signals. The most commonly used software, at least for beginners, is called SDR Sharp. It's a free program that you can download off of the internet. And with a little bit of configuration, you can start listening to radio signals of all different types, including just like music, local radio stations. You can be listening to those on your computer, or you can listen to other types of radio signals and APRS signals. All right, so I'm going to pass it off to Jim now. He's going to talk about space-based radio. So, Jim, take it away.
Okay, so you have your SDR, and you set it up, and you're ready to start listening for what's coming down from space. But there are a number of things that we have to talk about before that makes any sense, and before you can be successful. And that's really about the first thing we ought to discuss our orbits. So you can advance it one there. No. And orbits are a part of like math and physics and science, referred to as celestial mechanics. And basically what we're talking about here is this massive math problem. Once you fire a spacecraft off into space, it follows physics and math in a very perfect way. There are some other things that get in the way of its path, dust and maybe solar wind. But we've been really good at the scientists, and have been very good at calculating all of this using celestial mechanics, so they know exactly where the planets are and how to get a probe onto Mars. It's all celestial mechanics, and you're not going to be. We're not going to talk about the physics of it or the math of it, but if you're teaching math or physics to kids, here it is. It's like there's a real use for this, and we're using it very well. We're getting these orbiters onto the moon. So celestial mechanics deals with the big picture. Next slide there. But if you're talking about the area that we are more interested in is astrodynamics, and that has to do with artificial satellites. It's the celestial mechanics of artificial satellites. So, an orbit, a lot of us, the uninitiated, we think of an orbit as an orbit. It's going around in space up there, but that's not necessarily so. According to, celestial mechanics and astromechanics, we have some very different things going on up there. So one more there, So we actually have different kinds of orbits happening. And if you're going to be trying to speak or communicate with a certain satellite, you have to know something about what we're going to focus on, really the three specific orbits that affect these types of satellites that we're interested in. And one of those orbits is what they call the sun synchronous or polar orbit. And I know that the folks in Maine are really interested in this type of orbit. Maine is set up in a way where you can launch over the Gulf of Maine and achieve this polar orbit. And the thing that's kind of cool, it's kind of a rare orbit. There's not a lot of spacecraft using it. A lot of spy satellites in this type of orbit, but it basically goes over the same path of the planet at about the same time each day. Just and again, that's all the math. That's all the astromechanics there, the celestial mechanics. So that's one type of orbit. If you're going, hopefully, if you want to speak with a satellite or communicate with a satellite, get data from it that's in a polar orbit, hopefully it's going over your school at the right time each day. If it's going over, after school, you'll probably never see it. So you could get kind of frustrated if you didn't check out what kind of orbit the satellite is in. So sun synchronous is one of those orbits. Next one, Noah. The other one is what they call geostationary or geosynchronous, and they launch these spacecraft to an altitude and at a speed where they continue to they orbit with the planet. The weather satellites, if you've ever seen any of those satellite photographs, you get the same picture every time. Again, a very special orbit, a very high orbit, but it's basically parked right over a location on the in relation to the Earth. And if you are, well, you can actually download data from those GOES, geosynchronous satellites, and get your own satellite pictures. Some people like to do that. Okay, the next one. This is the third orbit that we're talking about. As you can see, there's some things you need to know about orbits here. Not a lot of details, but this is the one that we're most concerned with. Most of the satellites that we'll be utilizing are the LEO satellites, or low Earth orbit satellites. Most of the amateur radio satellites are in a LEO orbit. The International Space Station and the Chinese Space Station are all in low Earth orbits. So this is probably the one that you'd be concerned with. Now, there's another bit of information that when my kids, they were launching space shuttles, they used to, well, let's take a look at the next slide. They used to vary the LEO orbit by what's known as orbital inclination, and it's the angle across the equator at which they launched this satellite. And some of those, back in the days of the space shuttle, when I had communications set up in the classroom, the kids were all excited about talking with astronauts, and they would launch a shuttle at a 26-degree orbital inclination. And my school was at 43 degrees north, and 28 satellite or the space shuttle launched at 26-degree inclination would never come as far as our school. So we basically keep the radio station shut down during those missions. So you do have to take a look at the orbital inclination of the satellite. Make sure that it is launched at an inclination that will take it over your school. You might be tracking it and you see it, and it looks like it's coming your way, and then it never makes it to your school, and you might start to wonder, why aren't we seeing this satellite? And then if you check its inclination, you'll see that perhaps the inclination was too low for your orbit, for your place on Earth. So that's kind of some of the information about satellites that you need to know. And once we've found out about the type of orbit and inclination, then we need to find the ID of the satellite. Each satellite is assigned a specific number. It's cataloged and numbered, and knowing the number of the satellite will help you to locate it and help you to track it, which is the next part of what we're going to be doing here. And NOAA is showing us just all the different satellites that are up there. Um, a lot of the satellites that carry radios, if you take a look at the Oscar satellites, and they have their own numbering system. But the Oscars will be satellites that will be carrying amateur radio, and those are the ones where you'll be able to listen to. And if you go ahead and get your tech license, your amateur radio license, take your 30 question exam, and get the license, you can actually talk through the satellites. In my classroom, we talked with somebody in Mexico through one of the satellites that came over. That was one of the good communications that we had, just laid out perfectly. This guy talked with kids in the classroom, obviously from another country, a very pronounced accent. So success with an Oscar in my class. Okay, next slide there, Noah. I think, yeah, so for tracking, the one of the satellites one of the tracking programs that I used to use, and the beauty part of this is I had like the worst computer. I mean, it was one of the old computers that they had thrown out from the school, but this tracking program, and I'll put that address, the link to it, into the chat here. But this particular tracking program was very low level. It would work on very low level computers, and we just ran that tracking program in the computer, just set it up at the station and let it go. It had its own alarms. We set up alarms, and it would yell to us when a satellite of interest was coming over, and we would just shut things down and turn on the radios and make our communications or listen or whatever we were going to do. And then, and that's about, if you're lucky, you get about a 10-minute pass. That's one of the best passes that you'll get from an orbiting satellite. And the thing that's really nice about that is it is a little bit of an interruption in what you're doing, but the kids learned very quickly to get right back on target. We would take 10 minutes, maybe 15 minutes, set up, do our communications, and then go right back to the lesson. And they got really good at that, So a low-level computer tracking program is something that you'd want to have running in your classroom. The other thing that we would do is we would write down the times that our specific satellite that we were after would come over. And the kids started to find, again, mathematically, that there was a rhythm, a timing to the satellites. We found that the International Space Station would first appear over the school in the afternoon. And then gradually that orbit would decay into the middle of the day. And at some point, the last we'd hear from them for about a month would be the first thing in the morning. So, it's not so much when you launch something into orbit, it's not so much that it is moving around, it's traveling around the Earth up there. They fire these things into an orbit, and that's a fixed place in the sky pretty much. They have to boost the satellites every now and then to keep them in orbit, because it's really all about the speed. The low Earth orbiting satellites have to maintain a speed of about 17,500 miles an hour. And with that, they just continually fall over the horizon. So they're not really up there driving around. If they were to stop, they would be drawn back to Earth by the means of gravity. And it's once they fire a satellite up there and it starts into one of these orbits, when you track it, it might seem that the satellite is moving over different places of the Earth, but in fact, the Earth is rotating under the satellite, and that's what makes the satellite change positions, the fact that the Earth is rotated underneath it. So that 17,500 miles an hour, that speed, basically it's microgravity, it's free fall, and that's why our zero gravity flights, which is coming up in early May, that's why they stimulate space so well, because basically that's what's happening with the microgravity or weightlessness of space. So let's see. I think we're on to that next tracking, the next slide there. Well, do you want to go into a few other tracking programs there, Noah?
Yeah, while you were talking, I was kind of just going through the other two we have on there. So the first one you were talking about was GPredict, right?
No, it was actually STS Plus, and
Oh,
I put
okay. I
that
don't.
into. Yeah, it's a real old one, but the thing that's really nice about it is that low level computer capability with that one.
Right. And it's the same pretty much for all three of these on here. So GPredict was the first one I showed. That too is a very non-resource intensive program that can run on pretty much any computer. Um, Whereas these other two are web-based. So you have Heavens Above and you have n2yo.com. Both of these, I mean, pretty much any computer can run them because they're just on the internet. I particularly like n2yo.com, but Heavens Above is another good one. Where right here we could just click on ISS and it gives you all sorts of information. The nice thing about this one too is you can put in your location. So using browser geolocation should automatically locate where we're at. Yep, there we go. There's my house. And so then if we go back to home, go to ISS, it'll tell you when you're going to have the different passes. So what the date is and what the time is, just to, go outside and start, pointing your antenna up at the sky.
I think ISS is constantly beaming down. It could be pictures, it could be other amateurs, amateur radio operators speaking through the ISS to other ground stations, or the astronauts on board transmitting to the ground. So when the ISS goes over, there's something that you can hear from it.
Mm-hmm.
All right, no, that's kind of I think that's
All right.
28 there. So
All right. Yeah. So then we have an idea of how to track satellites, the different um, types of orbits that they have. And we talked a little bit about space weather and different types of radio wave propagation. So these are all factors that affect communications. So depending on where it is in the sky and where you are on the ground and what things are around you will determine whether or not you're in a good spot to pick up a signal from a satellite. So terrain is really important. As we had seen earlier, different types of radio signals will interact with terrain in different ways. So, you know, ideally, when working with satellites, you're going to have a wide open space. A good view of the sky that is unobstructed by buildings or trees or mountains or hills. So always keep that in mind if you're going to set up your own little ground station. Other things include space weather, as we had mentioned before, solar activity, whether solar flares or sunspots, but also man-made obstacles as well. High voltage power lines can put out interference as well. And if you have extremely sensitive equipment, that can be affected by things as mundane as light bulbs. I learned from Rocco just the other night. We were talking, and he was telling me about his very fancy um, LEDs light bulbs that don't interfere with radios. And he could tell you a little bit more about that in a minute. Um, the other things affecting your communications will be the type of antenna that you're using. So the length of the antenna is important, as well as the orientation of an antenna. The thing to keep in mind about satellites is that they're generally tumbling through space, and so that means that their antenna is tumbling through space. And in order to get a signal, your antenna has to be in the same orientation as the satellite's antenna. And so if it's tumbling and your satellite or and your antenna is stationary, you're going to get intermittent signal from that. And so one method that some folks will use is they'll actually be twisting their handheld antenna to try to turn it in line with the antenna up on the satellite, which, that's most certainly one of those finesse, skills based things. Um, but then, you know, after you've been doing this for years and years, you figure that kind of stuff out. So we talked a little bit about the International Space Station. So we talked about using that free software to locate and track it, and then there are different types of signals, as Jim had mentioned. Sometimes it'll be data that they're sending down. Sometimes it'll just be verbal communications. But you can listen in on those signals as well. And Jim had mentioned about the weather satellites as well. You can actually set up a ground station to download the data straight from the weather satellites. And so the exact same satellite images that your local weatherman is using on TV to show you what the weather is going to look like, you can also get that exact same stuff. Now, of course, it's simpler to go on weather.gov or weather.com and see it there, but it's a lot more fulfilling and interesting if you're doing it yourself and you're getting those signals directly from space. That's a really cool thing to do with your students, and it's like a real good feeling of achievement if you're able to do that. And there's all sorts of YouTube videos and websites out there that you can find the resources on how to make very simple antennas to download those signals. I mean, you can literally make an antenna out of um, wire coat hangers and 2x4s that can pick up those signals. So I had mentioned earlier about our orbital satellite Serenity. Here is some of that important information that you would need if Serenity was still available to communicate with. Um, we were talking about satellite IDs. This was the ID that Serenity had, as well as the frequency in order to actually communicate with it, was 437.0. Serenity had multiple sensors and experiments on board. I like to talk about the radiation sensor that was on there because that was made by a sophomore in high school. He came up with that experiment because he wanted to investigate how to protect future astronauts on deep space missions from harmful radiation. So luckily here on Earth, we have the ionosphere or the magnetosphere that blocks uh, cosmic radiation and keeps us safe. But once you start going, outside of that protective layer, if you're going to be going to Mars or go to an asteroid to start mining asteroids, or one day when we start exploring the outer solar system, we're going to have to figure out ways to protect people. Radiation is going to quickly become one of the most dangerous parts of space travel. And so this student at like 16 years old was thinking like, okay, maybe when I'm older, this is going to be something that's happening. And so generally in the past or currently, lead is the number one material used for blocking radiation. Unfortunately, lead is also extremely dense. And so in even small quantities, it gets pretty heavy pretty fast. And launching things into space is an extremely expensive endeavor. And so launching heavy lead objects is not really an ideal solution for radiation. And so he was looking at various different materials that might be able to also block radiation. And he settled on uh, lead zirconate titanate, also known as PZT. Um, and what that is it's still lead, but it's molecules of lead suspended in a gel-like material. And so he wanted to see, will just a number of molecules of lead be enough to actually block radiation. And so he took two pieces of fabric. He covered one piece with this gel, and then he left the other one alone so that it could act as a control, and put both of those on top of radiation sensors. And it's hard to see in this picture, but those sensors are actually right here on Serenity, these little yellow things right here. And so we first put that up on a high altitude balloon mission and found that it blocked about half the radiation. So that was pretty good. Um, then it went up on the Perlin stratospheric glider, and again, able to replicate that experiment, and it blocked about half the radiation. It went up on a Blue Origin suborbital rocket and blocked half the radiation again. And so then finally we put it on Serenity to see if up in orbit if it would still work. Now, unfortunately, as they say, space is hard, and we've had multiple opportunities to launch Serenity. The first being in 2021 on Firefly Aerospace's first flight, orbital flight. Um, it's not easy to launch things into orbit, and especially on your first shot. And so, a few minutes into flight, at about 14 miles up, the rocket lost control due to a engine failure, and they had to blow the rocket up, which included our satellite. A year later, they launched it again. We made another Serenity 2, and launched it in October of the following year, and it reached orbit, but unfortunately, it wasn't the orbit that they were aiming for. And so instead of Serenity staying up for weeks or even months, it only stayed up for a couple of days. Now, we were able to see the signal for it, but it was just not enough time to really acquire a signal. And so, we weren't able to download any data. Then last year, we launched Serenity 3. They made it to the orbit that they were reaching for. Unfortunately, what we learned at that point was that the satellite communications hardware that we had put into Serenity was not really up to the task. Unfortunately, the radio was just not strong enough to be able to send a strong enough signal down to Earth. So we weren't able to create an uplink and actually get data from Serenity. But we've learned a lot, and if there is a Serenity 4 one day, we know what we need to do to make that work, and hopefully we'll be able to test that radiation experiment up on orbit. So yeah, that's some of the basics of satellite communications using amateur radio. uh, Amateur radio is great because it's so accessible. um, pretty much anybody can take the test and get an amateur radio license. And what's even better is that there are amateur radio clubs all over the country that you can work with, you can reach out to. They'll help you get licensed, or they'll help work with you and your students to do this type of work. And with that being said, um, we've got a wonderful resource available to us in the form of Rocco Conti, who he was our ground station operator, and I'm going to let him kind of just discuss amateur radio clubs and what they are, how they work, and how you can get involved with yours. So Rocco, why don't you take it away?
Okay, thanks. Good evening, everybody. It's good to be here tonight. So amateur radio. First of all, it's more accessible now than it's ever been. Okay. As a matter of fact, a few weeks ago, we tested and licensed a 9-year-old little girl. She, dad was a ham, so had some help studying, but came in, tested, passed, was all excited. So very accessible. Most clubs in your area will be happy to help. You'll find that there's usual multiple clubs in different areas, and a lot of these clubs specialize in different things. So space communications, satellite communications, you'll usually find a club that's what they specialize in, or multiple things per club. Your best resource for that, for your area, is to go to the ARRL's website, arrl.org. You can just search find a club, and from there you can search by zip code or city name or whatever, and it will get you clubs in your area. If that doesn't work, you can always contact me, and I will find a club and a contact in your area for you. But we're at the point now where there's a lot of clubs are coming into the 21st century and giving online classes, online courses, and online testing. So a lot of people, you don't even have to leave your house. You can study online for free. There's a lot of free resources out there. You can study online. You can, take your test online, and basically you'll get an email from the FCC saying, okay, here, pay your fee, and then if you pass, obviously, and you'll know that, you'll get your license. So it's pretty simple now. It's easier, I think, than it's ever been. And as Noah alluded to, space is hard, right? So, but there's a lot of satellites up there, and you can take advantage of that. And believe me, those first contacts are great. I will tell you a quick story. Our first contact, we didn't have a lot of help, but we knew when this this orbit was going to be, and we had this handheld radio and a handheld antenna, and we ran out in the middle of the field there where Noah came and visited us, and we're standing out there, and Reed is holding up an antenna and he's turning it, and all of a sudden there was the satellite, and we could hear these people talking. Well, and so we managed to make that first conversation and make that first contact. And what we thought about was, all right, so we made it on basically a $25 handheld radio, $100 and $150 antenna, right? So for under $200, we made that first contact. And then that has gotten me to thinking recently, can we cut the cost on that? And we're working on the $50 ground station now. We've tried some different antennas. We've had some success. Unfortunately, I hate the cold, so I'm not good for standing out there on January and February nights trying to point an antenna in the air, but we'll get back into it. But we're thinking this is doable for $50. It's easily doable. Clubs are accessible. Again, arrl.org, and find a club. And if you can't, contact me. We'll get you in touch with somebody who can help you. And we can make the ground station available for folks as well. So there's always ways around it.
Another thing that the ARRL is really good at is funding teachers. They have a great summer program, and they also have a grants program for equipment. And by the time I retired, we had a state-of-the-art satellite station with antennas that, cost hundreds of dollars. And when you're doing satellites, you want to be able to track the satellite. We had a motor to move the antenna to keep track of the satellite. And that was a lot of that was funded by teacher grants through the ARRL. I believe it was the Victor C. Clark Youth Incentive Fund.
That is
so,
correct.
Yeah, if you're looking for money to do a little bit more with amateur radio in your classroom, they were really supportive of that. So,
and they're very supportive. ARRL is very supportive of anything that, number one, is STEM related. and anything where kids are involved, they really like that, and anything where multiple people benefit, right? So you've got you've got the perfect storm here to get grants, right? Because it's STEM, it's it's teaching, it's schools. Um, you've got the perfect storm for getting help from the ARRL. And there's a lot of resources too that aren't necessarily available. Um, that they're available, but they're not. It's really not public. They don't do a good job sometime advertising some of that. So if there's something specific that you're looking for, get a hold of me. I can get a hold of my contacts out there at the league, and we can see what we can do.
Yep. And if you're trying to get in touch with Rocco, feel free to send me an email. I could set up either a meeting, or I can give you his contact info, and you and your students can get all sorts of great resources through him.
Yeah, we can definitely do some demonstrations of the ground station. Um, I'm working on something to try to make the ground station a little bit more easily accessible. Um, so we'll work on that, because I think we have had it on now where when they do some of the slow scan television stuff, um, what I do is I set the ground station up to track the ISS, so that when it flies over, you can see the pictures being received and whatever. Before too awful long, we're going to have it set up so that um, classrooms and licensed hams, if they don't have access to a ground station, they'll be able to communicate through this one. So we'll get it figured
great.
out. Yeah, we'll get it figured out so that everybody, if there's a kid that wants to use a satellite and they get licensed, we're going to figure out how to make it so they can.
That's awesome. All right. Well, I'd like to open it up to questions now, if anybody has any for either me, Jim, or Rocco. If not, if you like often happens, if you think about the question after the meeting is over, feel free to send me an email, noah@tis.org, noah@tis.org. We are here to help you in any way that we can. We can help you find the resources that you need, whether that is funding or just pointing you in the direction